Greetings, Earthlings. So today we're going to take a look at the frequency counter, following on from our previous investigation where we discovered that one of the 5-volt regulators was only putting out 1.5 volts under load. So what I've done is I unsoldered the output of that regulator, and I've connected that to well, where it was feeding to this power supply, which is set to output a constant 5 volts, and it can supply up to what, 6 amps at least. At least 5. And so we're going to see how much current this thing actually draws under load. Well, I have current limiting set, so we won't let it go too high. But we're going to see, it looked like it was drawing over an amp because that, what is that? That's an LM-309K, which is specified to supply up to 1 amp at 5 volts. So it looked like it was drawing or wanting to draw over an amp, which would be a lot. And since I had measured the multiplier card out of circuit and it draws, I don't know, about 300 milliamps, it looked like maybe there was a problem with the input card drawing too much current. But let's find out. You can see on this meter over here, this is set to measure the current. That's 6 amps full scale, so 1 amp would be down there somewhere. And so if I power this on, I'll do these together. Okay, and there we are. I'm on 100 millisecond time base and times 1, so we have not switched in the multiplier yet, and that is drawing, well, from here it looks like about 600 milliamps, which isn't too bad. I'll switch on the output of my signal generator, put 100 kilohertz into it, and you can see I've got 100.00. Okay. So now let's switch in the multiplier. And watch that, and it should probably jump, and I gotta be ready to switch back to times 1 real fast if it jumps rather high, but oh well, it didn't. Oh, and look, it's working, 100.001. So that's up to about 800 milliamps, which is not bad. Let's go times 100. Will it take times 100 on 100K? Yes, it will. So 100.0000 or 99.9999, 9999, 4 nines. That's pretty good. And I just turned this on so it's not warmed up. So that says 800 milliamps-ish, which tells me now that we've got a bad regulator. Well, as I may have mentioned previously, I did get spare regulators. I bought 6 of them. 3 of them looked like this, and then 3 of them looked like this. These are newer, I think. These have a 1983 date code. These are can't tell. I don't even know if that's a date code on there. But what it looks like is that regulator is not up to spec, and so I'll replace that and we will proceed from there. Let's just, I mean, with no load, you know, it was at 5.04 volts or something like that. Yeah, it's fine, 5.05 under no load, but at this load, it can't hack it. Yeah, so I'm going to swap that out and see if we can't get this working without an external power supply. All right, this is weird. I'm on my fourth one here. This is the one I took out. And then I tried this one, and I tried, which is matches, right? It's the same look as the original one and date code. Then I tried a steel one, and this is another steel one. I'm down to, well, I have 5 total because I bought 6, and there was number 6. But watch this. Power on. Now I'm 100 milliseconds times 1, right? 100 kilohertz. If I now switch to times 10, it doesn't like it. And I've got 1.5 volts. Okay, it's consistent. Okay, but switch off. Let me switch on at times 10. There it is, 100.00 whatever. .05 volts. So what is going on? Remember that the 5 volts is not sent to the multiplier board unless something other than times 1 is selected. So when we're at times 1, we're only powering the input board. And that's drawing whatever it is, well, whatever it was, 400 milliamps or something. Then when we switch the power on to the multiplier board, we lose it. It locks out. Now, I wonder, there's a whole lot of tantalum capacitors. They're not, I mean, it's not an issue that they're tantalum. It's just that there's a whole lot of capacitance across that 5 volts potentially, which means that initially it may want to draw an excessive amount of current when you switch it on. So it could go over an amp. If this regulator locks into, you know, lockout mode, as it were, then that's a problem. But that doesn't explain why, if I power it on in times 10 mode, it's happy. Okay, and here's another issue. It is locked, but the unlock light is dimly lit, and that's because I replaced the incandescent light with an LED, and so that's driven off of a logic output. And the logic output is mostly high, but then it occasionally drops. So when it's locked, it still goes out of lock periodically, and so there are these very short spikes on it, which are not being filtered out. With an incandescent light, they're just filtered, you know, sort of thermally. They'll provide not enough current for that for the filament to light up, but enough for it to just enough to keep it warm, you know. So a fix to that is so in the circuit. If we look at the circuit, it is so. This is what drives turns the the counter on so that it can actually count. Sends the output to the counter. And it's got a filter on it. There's a 2.2 microfarad capacitor. So this resistor and this capacitor form a low-pass filter. Okay. We're down here, and we have no capacitor, so there's no low-pass filter on this line. So the solution would be to put a capacitor there to provide a low-pass filter, keep that transistor from turning on, and that would be fine. But that's the least of my worries at the moment. All right, so here's what I've done. I have made a 0.1 ohm resistor here. This is just a length of 26 gauge wire that I measured out to 0.1 ohms. Doesn't have to be exact, because the exact thing doesn't matter, but it's pretty close at this temperature. We won't even talk about temperature coefficients and all that kind of stuff. And I've got an active probe here. So that is in line from the regulator to the feed to the boards, okay? I've got an active oscilloscope probe. I've got the digital scope out. And what I've done is I've set this to times 100. So it's a times 10 probe, and then it's 0.1 ohms, so add another factor of 10, and we will read directly whatever it reads as the voltage level will be the current that's flowing, okay, that those two boards draw. So I'm at 100 milliseconds, times 1, power on, and it's about 800, and there's a lot of noise here, but it's showing about 820 millivolts, so that's 820 milliamps it's drawing, okay? If I'm going to switch off, I'm going to switch on times 10, and so here it is with both boards powered, and that's very close to 1 amp. It's showing about 990, occasionally ticking over 1, but you know, there's noise. There's enough noise there, but it's about 990 or so, so it is very close to 1 amp combined. Switch down, 820, 830-ish. Now switch back, and I want to see what happens. And something very strange happens. Very, very strange. That's always the wrong button. I always pick the wrong button. Okay. So it's gone into current limiting, so it's at 250 milliamps average. But look at this spike. And why does it go negative like that? Oh, well, I'm starting to think at this point that it has something to do with these capacitors. So when you're on times 1, the +5 line on the frequency multiplier board is grounded. So those capacitors are fully discharged. There's 447 microfarad tantalum capacitors there. When you switch to times 10 or times 100 or times 1,000, that switches to 5 volts. Those capacitors have to charge. They're going to want to draw a lot of current initially because they're fully discharged. So that could be something we see. And then when it shuts down, maybe this is the capacitors discharging back through the regulator, which is not good for the regulator. So how to deal with this? All right, for my next attempt at making sense of this thing, what I've done is I've soldered the input board's power feed to the voltage regulator, and I've got the power feed to the multiplier board coming from this power supply. And that's hooked up through my little 0.1 ohm resistor so that we can look at it over there and try and see if try and see which board is causing the problem, I guess, is what we're trying to see here. I do have to plug this in. Okay, there is one potential issue, and that is that this is the multiplier board, and this is the switch that switches between ground and +5. And there is one feed to an input here on the input board. It's just a logic signal to an ECL gate. That's IC-404. So that could be the problem rather than something on this board. Unlikely though. I did try, the IC-403 and 404 are the same part, so I did try swapping them, and the behavior didn't change. So we're going to proceed here. So power on. Okay, 100 milliseconds times 1. Do I need this power? I guess I need this power. Or did I hook them up right? Now I wonder. Well, let's try switching. See what happens. It works. Okay. So a possibility is to add another regulator. And I would use like a 7805. Fit it in here. And, just see if that solves the problem. Apparently we're running too close to the limits of this regulator, making me ask, did it ever work? It may be that this board, the input board, is for some reason drawing too much current, or more than, it was intended to. Tracking that down would be hard because it's working. I can do a finger test. That's hot. That's quite hot. Whoa. That's hot. Yeah, those ECL chips are all running hot, but that's expected. These transistors, not so much. I don't have one of those fancy, FLIR cameras. Okay, and here we are. I looked through my parts. The best fit I had, I would have liked to have found a 78M05. I didn't have that. I had a TL780-05 KCS, which is 1% tolerance. It's a better 7805, really. So that's mounted here. I took 5 volt. No, this is the unregulated input. That goes to the in. The ground is actually the tab there. So that's grounded to the TO3, through the TO3 case of the other regulator. And then the output here is that lead which goes to this board. So let's see what happens. I'm going to tilt it down here. And I've got my voltmeter ready to measure voltages. So we start on 100 milliseconds times 1. Okay, we have to plug it in. It does help. Okay, we start on 100 milliseconds times 1, and we power on. And 100.00, that looks good. Okay, I am going to check that LM309. That's the one that's feeding the input board. That's saying 5.08. And I'll check my new regulator. And that's saying 5.00. Ooh. Spot on. Okay. Of course, it's not putting out any current at the moment. Okay, times 10. It works. So 309, LM309, 5.08. The new regulator, 5.00. Oh, and the other regulator, just for the heck of it, 5.05. Okay. Well, at this point, I do want to look at adding a capacitor to filter that. But otherwise, it's good. I can't really explain why it needed this extra regulator if it ever worked, you know, as it was from Heathkit. So there may be another problem in here which will present itself somewhere down the line if something is, you know, drawing too much current, and it may fail down the line. And then I may say, oh yeah, well, okay, that's why it was drawing so much current, you know. But for now, it really seems to be working. What if I go 1 second? Oh yeah, well, I've got to do the final calibration. Once it's all back together. But it's pretty happy here. Alright, and it's been warming up, running for about an hour now or more. Have it connected to the 10 megahertz oven-controlled crystal oscillator. And it's looking pretty good. Plus or minus 1 count at 10 megahertz. It runs quite warm. About 47 degrees Celsius. And touching the case, it's really that's quite warm. But it's working. Oh, and I did add the capacitor, just a 4.7 microfarad capacitor as a low-pass filter on that lock signal. And so you see that the light, it is now locked. What am I at? 1 kilohertz, right, and times 1,000. But if I crank it up, there you see unlock is on.